record on this computer? All righty, ladies and gentlemen. So we are going into chapter 4, which is all about angles, and it's all about trigonometry. Chapter 4 and chapter 5 are pretty much going to be all trigonometry. So we did a little bit of the functions part of FST. We did a little bit of the statistics part of FST, which was our linear regression and our quadratic regressions, essentially chapter 2. And now we're going into the trigonometry part of FST, okay? And after the trigonometry part, we might bounce back to functions again, but that's depending on time. But let's focus on our trigonometry here, okay? So we have our 4.1 magnitudes of rotation and measures of arcs, okay? Our objective for today is that students will be able to understand and use magnitudes of rotation, convert between degrees and radians, and use the arc length formula to solve problems as taught, okay? So today's focus is actually only part 1. So it is this part right here, from here to here. Students will be able to understand and use magnitudes of rotation. Thursday, we will focus on convert between degrees and radians and use the arc length formula to solve problems, okay? So that's Thursday's focus. Today's focus is the first part, magnitudes of rotation. So let's review a little bit of vocabulary before we head out, okay? So this is essentially coming back to you from geometry. The last time I think we really talked about rotation other than function rotations. But the last time we really talked about rotation was during geometry. So just a reminder, a rotation is a transformation where each point is moved a certain number of degrees or radians, centered around a specific point. Now that specific point is called the center of rotation or the vertex. Okay, so the center of rotation, the vertex, is the point at which the transformation is being rotated. So essentially, like if you, here's your center of rotation, and then you take this and you're rotating it around the center of rotation. You can see is my hand. I apologize for that. I was trying to be clever. And then you have rotation image. Okay, so the rotation image is the new point or set of points that occur as a result of the rotation. So if you guys remember, right, whenever we did transformations, we had the pre-image, which was the starting point. And then we had the image, which was the ending point. So our pre-image was the original, okay, and the image was the final result. I hope we're good so far. I would ask for a thumbs up, but I've heard that a lot of you guys have done the Zoom update and you can no longer access the thumbs up now in the participants window for some reason, which I don't understand. Wait, I can't. No, I can still access it. That's weird. Maybe I haven't done the update yet. Okay, so let's take a look at the following. It says understanding angles. Okay, so when we talk about angles, we want to remember, again, a little bit of geometry, because remember, the first time you were introduced to trigonometry was in geometry, right? We had a giant, like a whole chapter on it. It was incredibly important that you understood it. And I'm pretty sure that when you had me for geometry, I specifically said this chapter is really important because this is going to come up in algebra 2. It's going to come up in every level of math that you do up, following that. So it's incredibly important that you remember your trigonometry, okay? And you remember angles, because now trig isn't just about right triangles, as you might have seen, as you definitely saw in algebra 2, right? Trig is more than just right triangles. Trigonometry is actually used in almost every level of mathematics, higher level mathematics, and in the way that it is mostly used is through angles versus right triangles, okay? So if we take a look here for our angles, right? An angle is when two rays meet at a common endpoint. Okay, so the most basic definition of an angle, when two rays meet at a common endpoint. So when we talk about magnitudes, right, it is important to remember two things about angles, right? You have two rays, but we determine magnitude by knowing which ray is the initial side, aka the starting side of your angle, okay? And then which ray is the terminal side, aka the side where it ends of your angle. And so in this situation, this means that our angle, okay, started here and went that way. Okay. Now, in the case of like magnitudes of rotations, or in the case of an XY table and trig and your unit circle, right? The standard position of an angle usually means that our initial side is the positive x-axis, okay? So essentially the positive x-axis of quadrant 1. So standard position means that our initial side is the positive x-axis here. And then however much we rotate, that takes us to our terminal side here. So however much we end up rotating, starting from the positive x-axis and rotating all the way over to our terminal side here, okay? So standard position essentially means that the initial side is the positive x-axis, okay? Now, depending on the direction of rotation, okay, that tells us our positive angle or a negative angle. So our initial side doesn't change from standard position. It is our positive x-axis here, okay? Here's our positive x-axis. This is the initial side. Now, if an angle is positive, that means it rotates counterclockwise, which means it goes upward and rotates counterclockwise. So this way, right? So it rotates that way. So our terminal side would end up being wherever it does. But what's important is that the rotation is counterclockwise. Now, if our angle is negative, okay, if our angle is negative, that means we're rotating clockwise. So we start from the initial side again. That doesn't change just because it's negative. But now we're rotating in a clockwise fashion this way. Okay, so we go downward. So if it's positive angle, then we start moving toward positive side in the Y. If it's a negative angle, we start moving in the negative side in the Y, right? So counterclockwise and clockwise. That makes that actually is very important, okay? Now, Okay, so can I get a yes or a no? Are we doing okay with these terminologies so far? Okay, let me get a yes or a no in the participants window, please. If you're unable to mark a yes or a no in the participants window, please give it to me in the chat like Juan just did. Thank you, Juan. Thank you, Anthony. Thank you, Ariana. Thank you, Juan. Thank you, Lumeria. Thank you, Kai and Nick. Thank you, William. Thank you, Wally, in the chat. Okay. Thank you to Aaron. I think I got everyone. Just V2 and Zon. Okay, V2 and Zon. If it's a no, if you have questions, that's fine. Just give me some indication or type in your question. But you got to give me some kind of indication. A no is okay. A no is totally fine. A no is wanted. Thank you, V2. I didn't see the thumbs up. If you put it in the reactions, then I definitely don't see it because it disappears very quickly. Thank you, V2. Appreciate it. All right, and thank you, Zon, for that feedback as well. Okay, so then I can speak, I promise you. This brings us to revolutions. Okay, so revolutions are essentially, each revolution is one full circle around. Okay, so when they ask you like how many revolutions, they're saying how many times did you go a full circle. You know, a lot of times they calculate tires and how many revolutions that a tire turns based on the speed and such. You know, car lingo. They also use that to calculate distance and things like that. So, you know, it comes up in a few interesting industries as far as the revolutions. All right. So we have a few more definitions here that we want to take a look at. That's actually quite important. Okay. So the magnitude, okay, the magnitude of an angle is the actual measure of an angle. Okay. So we don't just call it the measure anymore, it's the magnitude. Okay. How many degrees or how many radians is the angle itself. Okay. So the magnitude is literally just a measure. A revolution, okay, not like revolution as in what just happened last week, but or what tried to happen last week. A revolution in this sense is a rotation in a full circle. Okay, so either 360 degrees or 2 pi radians, right? So a full circle. And then of course we go into some more detailed and almost intuitive words. Half revolution, right? That means that that's a rotation that is half of a circle, so it makes a straight angle 180 degrees or pi. You guys remember? And then you have a quarter rotation or revolution is a rotation that makes a right angle, so 90 degrees or pi over 2 radians. Okay. So what do we do when we have an angle with a magnitude? And we're asked to find the angle between 0 degrees and 360 degrees. That corresponds to the given angle with the given magnitude, okay? So the first things first, we want to figure out what is the angle that corresponds to 0 degrees and 360 degrees, okay? Or between 0 and 360, in this case, because we're dealing with degrees, right? Our next examples will be in radians, okay? And then we want to actually like graph the angle. We want to show the angle. And I'll show you guys how to do that as well. But first things first, we want to figure out what's the angle that corresponds to 1,275 degrees. That's between 0 and 360. And so the simplest way to do this is you essentially take your angle, and because it's greater than 360, right? We can definitely see it's greater than 360. We can start subtracting 360 degrees from it. Each time we subtract 360 degrees, that's one revolution, right? So if I subtract 360 degrees here, that's going to leave me with, hold on. Okay, divided by 360. Okay, so that's not divided by, did I just do that? That is silly of me. There we go. So that leaves me with 915 degrees. And then I'm going to subtract another 360 because this is still greater than 360. So there goes another 360, and that leaves me with 555 degrees. And then I'm going to subtract another 360 because that's still greater than 360. And that now leaves me with 195 degrees. Okay, so 195 degrees is between 0 degrees and 360 degrees. So this angle, what does this mean? This means that the angle of the 1,275 degree angle and the 195 degree angle share the same terminal side. Okay, they share the same terminal side. So do this 915 degree angle and this 555 degree angle. So all four of these, okay, all four of these angles right here, they share the same terminal side. The difference is how many revolutions it takes to get to that terminal side. Okay, so as far as our revolutions are concerned, we start with a XY. Okay, here's my X, here's my Y. Okay, here's my initial side, always from standard position. This is my initial side. Now, I subtracted 1, 2, 3 360s. That means when I am graphing this angle right here of 1,275 degrees, before I can get to my terminal side of 195 degrees, I need to make 3 revolutions around. I need to go 3 times around in full circle, okay? Now this is positive, so I am going this way, okay? And my terminal side will be at wherever 195 degrees would be here, okay? So if I take a look, if you guys remember, right, this is 0 degrees, this is 90 degrees, this is 180 degrees, 270 degrees. So if I'm looking at 195, then I am looking at something around, this is 180, so 190, 195 is approximately going to be somewhere around here, okay? And it's a guesstimation. It's not like, it's not, you know, exact science here. I don't need you guys to bust out a protractor. Let me put it to you that way, okay? So what happens here? Okay, how do I graph this 1,275 degree angle? Okay, so I start on my terminal side and I start making a circle in the positive direction because this is a positive angle. Now, if I were to stop at my terminal angle here, that's my 195 degree angle. But I don't want to stop at my terminal angle because I'm graphing this guy. So I'm going to continue on. That's one full revolution right there. If I bring that further and bring it to my terminal side again, I have just graphed this angle right here, 555 degrees, because I went a full 360 plus the 195. Okay, but again, I continue on. Now that's a 2 full 360s, continue on to the 195. I have now graphed 915 degrees. Okay, notice I've gone around 1 full revolution, 2 full revolutions, and the 195. Okay, Now, if I take this to the third full revolution, okay, and then bring over the 195, this is now my 1275 degrees. Why? Because I have 3 full revolutions. So 1, 2, 3 full revolutions plus the 195 degrees there. Okay, so this right here is our 1270 degree angle. Okay, and that's the graph of our angle right there. Now, questions so far? What are your questions? Give you guys a few seconds to maybe think and see if you have any questions. I really slowed down that explanation. I'm sorry if that was tedious for some of you guys, but I feel like others need it. Therefore, we have to compromise. Okay. Okay. So if we take a look at the second example here, okay, this one's a much smaller degree, but notice it's negative. Okay, so it's a negative 17 degrees. Now, a negative 17 degrees, okay, if it's negative, then instead of subtracting 360, I'm going to add 360 until I get to the positive number, the positive angle that's going to be between 0 and 360 degrees. So I take negative 17 degrees and I add 360 degrees to it. So that's going to be negative 17 plus 360. Then that's going to give us 343 degrees. Okay. Now, because negative 17 was so small, all it took was really one adding of 360. So the corresponding angle here, okay, is 343 degrees. So again, what this means is that negative 17 degrees and 343 degrees share a common terminal side. Okay, they share a common terminal side. Okay, so because of that, when I graph the negative 17 degrees, the terminal side is going to be essentially the same. Okay, so my initial side is right here. This is my initial side again. So my positive x-axis, right? There's my x and my y. Now, 343 degrees. Again, remember that this is our 90, this is our 180, this is our 270, and then this starts at 0, but it's also the full 360, right? And so 343 degrees is going to end up being between 270 and 360. It's a lot closer to 360 than it is 270, right? So this terminal side is going to be somewhere around here. Going to be somewhere around there. Now, if I'm graphing negative 17 degrees, negative 17 degrees would mean that I would start at my terminal side, and instead of going this way, okay, my negative 17 degrees goes this way. So this is my negative 17 degrees. But if I graph the positive 343 degrees, then that would be that guy right there. Okay, and so this would be your positive 343 degrees there. So if you went negative, that would be it. If you went positive, that would be it. And again, we don't show those revolutions because there weren't any real revolutions. Okay, they essentially end at the same terminal side here. All right. I want you guys to think about some questions if you have any, and flip over to the back of this. Okay. Go ahead and flip over to the back. So now we're looking at, we're going to do the same thing, but now we're doing this in radians. And so because it's in radians, we're going to have to make sure that we are conscious of fractions. Okay. Thank you, Will, for letting me know. We're going to have to make sure we're conscious of fractions because radians are not as simple to work with as degrees. Okay. So we're going to do some examples, same idea. Okay. We're going to do some examples with some radians. Okay. So the radian is a different way of measuring a circle. Okay. Our radian measure can equal our arc length over our radius. But this also gives us our arc length formula, right? Arc length. So this is our arc length formula that we're going to be using next Thursday. This guy here. Okay. Arc length formula. Okay. Where S is our arc length and R is the radius. And then of course, theta is our angle in radians. Okay. Now, if you guys remember the article that you guys read about radians, right? The radian is essentially the measure of your circumference, the ratio of your circumference versus your radius. And so it's a different way of measuring an angle. It definitely uses your arc length, right? So if you remember, it was essentially this guy right here. What are radians, right? So, okay, it's essentially how many times your radius goes around your circumference. Okay, I was trying to find the words for it. Apparently my brain was not finding the words for it. It's how many times your radius goes around your circumference. And what they found was that's actually a constant number. Okay. Your radius, no matter what size your radius is, your radius will go around your circumference 6.28 times, which essentially comes out to 2 pi. 2 times 3.14, which is 2 pi. Okay. And so you have this nice little graphic here of what a radian is. So if you have your radius here, here's one instance where your radius is on the circumference of your circle, which calculates it as a 1 radian. So if we count it this way, that's 1. Okay. And then you would do the same thing. You would take your radius and do it one more time. That would be 2. One more time, that would be 3. And then 4. And then 5. And then 6. And then that would be your 0.28. Obviously, I estimated there. So over here, 2, 3, 3.14, that gives you your pi radians, right? So that's why we have pi here at the 180-degree mark. But then if we continue on, do they have one that's like full circle? No, but we can see that here, right? 1, 2, 3, 4, 5, 6, and then we got that little bit left right there, which gives us that 0.28, which comes out to about 2 pi. Okay. So radians are how many times your radius goes around your circumference, right? So it's important to understand the importance of radius. Okay. Give me one quick second. All right. So some places where our radius plays a factor here, we have our circumference, but I'm going to move on here. So if we remember correctly, right, we have this important information right here, okay? So 360 degrees is equal to 2 pi, and 180 degrees is equal to pi radians, okay? So one pi is equal to 180 degrees, okay? So when we want to find the angle between 0 and 2 pi that corresponds to these given angles, it's the same thing as asking 0 and 360 for degrees. And just like we were adding or subtracting 360 to the angles to get the corresponding angle that's between 0 and 2 pi, we need to now add or subtract the equivalent of 360 degrees to these radians here, which is 2 pi radians. Now, if you know, radians are notoriously fractions. So when I subtract 2 pi from 47 pi over 3, that means that I need to make sure that I'm subtracting correctly with fractions. Now, how do I know 47 pi over 3 is not between 0 and 2 pi? Because if I do 47 divided by 3 and it's anything larger than 2, that means I'm over 2 pi. So obviously we know that 47 divided by 3 is going to be larger than 2. It's actually significantly larger than 2. Okay, so we're going to have to subtract quite a number of 2 pi's. But if you remember, when we add or subtract fractions, right, we have to have a common denominator. We have to have that common denominator. So if I am subtracting from a fraction with a denominator of 3, that means I need to take 2 pi and turn it into an equivalent fraction that has a common denominator of 3. So I put my 2 pi over 1, okay? So I want that common denominator of 3, so I'm going to multiply top and bottom by 3. And that's going to give me 6 pi over 3, right? So 6 pi divided by 3 is 2, and so on. So 6 pi divided by 3 is the equivalent of 2 pi, but just with a common denominator of 3. So I'm going to take my 47 pi over 3, and I'm going to subtract 2 pi from it, but in the form of 6 pi over 3, so that I can actually subtract them, right? So this is going to equal 47 pi minus 6 pi is 41 pi over 3. I'm going to subtract another 6 pi over 3 because 41 divided by 3 is definitely larger than 2. Okay, we might end up doing this quite a few times actually. If you figure out exactly how many you need to subtract, you can just do a multiple of that, right? Make a shortcut for yourself. So this is now going to be 35 pi over 3. Okay, minus 6 pi over 3 one more time. Okay, this is going to be 29 pi over 3. So essentially, if I want this less than 2 pi, I need to have a number that is less than 6 at the top, right? So I got to keep going here. Keep subtracting that. So that's going to be 23 pi over 3. If I'm making any mistakes on my math, please let me know. Subtract another 2 pi. That's going to be 17 pi over 3. Subtract another 6 pi over 3. Okay, that's going to be 11 pi over 3. I'm getting close here, ladies and gentlemen. Subtract another 6 pi over 3. 11 pi minus, oh, sorry, that is way down. 11 pi minus 6 pi is going to be 5 pi over 3. Oh boy, finally. Okay, so we finally have the corresponding angle that is between 0 and 2 pi. And I know this because this number right here is less than this 6 pi over 3, right? Because this is our 2 pi. So any number less than this 6 pi is going to be less than 2 pi there. So how many revolutions is that? Oh boy, that's 1, 2, 3, 4, 5, 6, 7 revolutions total. Plus another 5 pi over 3. So this is 7 revolutions. Or that we're going to have to go around with a graph. And again, every single one of these angles shares the same terminal side, right? They share the same terminal side. Now, one of the difficulties that kids have when it comes to graphing radians is figuring out, okay, where does 5 pi over 3 actually go? Because I don't know, right? And what might help us is remembering what each one of these axes represents here. So this is obviously our 0. This is going to be pi over 2. That's the same thing as 90 degrees. This is going to be our pi. That's the same thing as 180, right? And then I believe this is going to be our 3 pi over 2. And then this is our 2 pi total, okay? Now, if you want to figure out where this is going to go, okay, 5 pi over 3. Now, that's definitely greater than pi, right? Because 3 pi over 3 is pi. So 5 pi over 3 is definitely greater than pi. Does it go here or does it go here? Okay, so is it going to be in quadrant 3 or quadrant 4? And so there's an easy way to check that. 3 pi over 2, okay, 3 divided by, that's the same thing as 1.5 pi, yes? Because 3 divided by 2 is 1.5. So if I figure out the decimal equivalent of 5 over 3, excuse me, okay, that's 1.67. Okay, that's 1.67. So this is the equivalent of 1.67 pi. Notice I'm not multiplying in the pi, I'm just getting the decimal of what this represents here, okay? So 1.67, that means it is larger than 1.5 pi, okay? And this is 2 pi, so 1.67 is going to be somewhere around here between 1.5 and 2. I hope that made sense, okay? So you figure out the decimal coefficient, okay, in front of the pi, and then you determine what it's between. So if it's greater than 1.5 in this case, then we're going to be in quadrant 4 here, okay? So our terminal side doesn't change just because we're in radians. Here's our terminal side, okay? Our terminal side starts here, and I'm sorry, that's our initial side. Ooh, backtrack. Our initial side does not change, okay? Our terminal side, however, is going to be at 1.67 pi. So 1.67 pi is really close to like 1.7 pi. If we just use proportionality here, this is going to be our terminal side here, okay? Now, we have 7 revolutions to go, okay? 7 revolutions. So we start here, okay, and it's positive, so we're going in the positive direction. So I have 1 revolution all the way to 2 pi, right? 2, 3, 4, 5, 6, 7. That one got eaten there. 7, and then the 5 pi over 3. So 7, and 5 pi over 3. Okay, so this is our 47 pi over 3. So 7 revolutions, and then our final 5 pi over 3 stops at the terminal side right there. Okay, I know it looks like a swirly. Yeah. So that's that one. Yay. Big numbers, right? And then we have our negative angle here. And again, once again, it's a smaller negative angle. But again, because it's negative, instead of subtracting 2 pi, we're going to be adding 2 pi. And so once again, you want to remember common denominators. So if I have 2 pi and I have a common denominator of 4, put that over 1. Okay, and you're essentially multiplying top and bottom by your common denominator, right? So we're gonna multiply top and bottom by the denominator that we want, okay? And so this is gonna give us our 8 pi, 4 times 2 over 4. So 8 pi over 4. And so we just take this negative pi over 4, and we're gonna add 2 pi to it in the form of 8 pi over 4, okay? There's equivalent fractions, right? 8 divided by 4 is 2 pi, or 2. So we're going to add that, and we will get our positive fraction here, which is going to be 7 pi over 4. Okay? That'll be 7 pi over 4. 7 divided by 4, once again, if you want to check to see if is that actually between 0 and 2 pi, right? 7 divided by 4 is 1.75. So that's less than 2 here. Okay, so 1.75 pi right there. Just to have our decimal reference. Okay. So over here we have our x and our y. X, y. And remember, this is our pi over 2. This is pi. This is 3 pi over 2. This is 2 pi and 0, right? Similarly, if we really think about it, this is the same thing as 0.5 pi. This is 1 pi. This is 1.5 pi. And this is, of course, 2 pi. So if we have 1.75 pi as our positive, okay, here's our initial side. And 1.75 pi, or 7 pi over 4, okay, that's between 1.5 and 2. It's actually smack dab in the middle. So there is our terminal side. So if I were to graph my negative, so my negative angle here of negative pi over 4 starts at my initial side, ends at my terminal side, and I go in the negative direction. So this is my negative pi over 4. Okay. The positive version of this starts here and goes to the terminal side from the positive direction. So this is the 7 pi over 4, the positive 7 pi over 4. Okay. That's it for today's notes as far as like me doing examples or giving you information. So the rest of the period we are spending, and we want to focus on our 4.1a classwork. So you have 4 examples, four problems to do of converting degrees. So convert each angle between 0 degrees and 360 degrees. Remember that if it's positive, you're subtracting. If it's negative, you're adding, right? Until you get to a positive. And then you have 4 problems with radians. Okay, so you want to convert each angle between 0 and 2 pi. If in my examples I graphed each angle, do you think I'm expecting you to graph each angle here? Is there an expectation that you are graphing each angle? Yes. Good. Thank you for those of you that responded in the participants window. Thank you for those of you that responded in the chat. Okay. So yes, you are to graph the angles here as well. Okay. So you're finding the angle, but not only that, you are graphing the angle. Okay. So for the rest of the period you are working on this, that means you have until 10:20. That's 30 minutes to do 8 problems. That also means 30 minutes to get help and ask questions. Okay. Um, so please do not hesitate to ask for help. Do not hesitate to, you know, get questions answered. If you would like to be put into a breakout room and work with someone, let me know and I will put you in a breakout room. That is totally fine. You know me, I'm all about collaboration by choice. And so if you want to work independently, work independently. If you want to work collaboratively, work collaboratively. Um, just let me know who you would like to work with. Okay, we have that freedom in this class. So um, I am here. If you have questions, please do not hesitate to ask.